Welcome to the fourth video of these presentations about how we can convert a continuous function into a step function. Okay, so we started on the first video about how we can make a real number a step function, a regular step function, or staircase functions, wherein we have the desired length, which is the h, represented by h. Okay, so if you have 5 right here, so we'll have exactly an constant interval of 5 units on the staircase. Okay, as we can see. Okay, so we also try to use this one in converting the linear continuous function into a linear step function, and also we work with the the standard form of quadratic equations and convert that one into quadratic step functions. So right here on this time we'll be converting exponential functions into exponential step functions. So from the nature of exponential functions wherein we have a base, then we'll try to raise this one into a real number value of x. Along the x-axis, you can see if we have the base which is equal to 1, then of course it will be just a constant value, because if we have 1 raised to any value of x is just the same value of 1. So but if we have greater than 1, so our function will try to increase rapidly or exponentially. So we have now doubling value because we have base is equals to 2. Okay, so let's say for example we want to convert this one into exponential step functions. So using our properties of converting an integers or the real numbers into integers, and or the real numbers into desired length of step functions. So we'll be focusing only on the exponent, wherein the exponent is any real number, and we'll try to convert that one into a step function. Okay, so we'll try to rewrite this functions of x. Then we have equal to, so we'll try to copy just the same base, and we'll try to raise this one into our converted step function. So we have h, and then we have the floor of x divided by the desired length of h. Okay, then we'll try to put some h length. So you can see that our exponential step functions follow exactly on the nature of how this continuous function increase. Okay, so if we have 1 unit, you can see that we'll have 1 unit. Okay, so it is a constant length of step functions, and then if we try to drag this h, moving it into 3.6, you can see that the length interval of this one is also 3.6. Okay, and these step functions will try to move exponentially only if it reach a certain interval of desired length, which is 3.6. Okay, and if we try to decrease the exponent, so let's say it's like this one, and you see it's also try to follow the same pattern. And if we try to increase the length, or we try to decrease the length, or if we have on the negative side, it will try to move on the other side. So the floor function now is being converted into a ceiling function. Okay, so if we have the value of a, it's less than 1, and it's supposed to be exponential decay. Okay, and you can see how the decay works. Okay, and then we have also uh, some exponential function that there is some coefficient value. Okay, so let's say we have a coefficient of a p value, that one p. Okay, and we'll try to also do the same right here on our step converted step function. So if we have a p which is 2, I'll see that right on 2. Okay, see, and if we try to check, we are on 2, and then the step function will try to decay every 3.4 unit. Okay, so if I try to decrease this step function 1.2, so it will try to decrease or decay every 1.2. So that's it for exponential step function. I wish to extend also this application not only on exponential, but uh, on the next video I will be showing how we can convert trigonometric functions such as sine, cosine, and tangent function into a step function. Thank you so much, and hope to see you on the next video.